VIT, a place to learn, a chance to grow.
Hello friends, welcome back to this lecture series on process dynamics and control. In this lecture we will see how to develop the mathematical model of a nonlinear process, and then we will see how to linearize this around one operating point.
MATLAB. Let's go to the course. First, we will see the methods available to perform the nonlinear system analysis. In nonlinear approach, we can simulate the nonlinear system equations using analog or digital tools and numerically compute the solutions. And we also have a linear approach where we are going to find the transformation of variables using some approximate linear transformations, and we will be building linear models in the neighborhood of some specific operating conditions. So if you know the specific operating point for the nonlinear process, you can find the approximate linear model around that operating point, and you can do the control system design and analysis. So linearization is the process of approximating the nonlinear system with linear system models. So we will see why we should linearize the process. So the first thing is, if we can linearize the model, then we can analyze the process behavior independent of the input variables and other process parameters. And also, most of the effective control system designs are limited to only linear systems. So we have to linearize the nonlinear model around the operating point, and then we can design effective control systems. So it is necessary to do linearization. So in this lecture, we'll see how to build the linear model from a nonlinear system using Taylor series. So in Taylor series, we'll see a single variable case and two variable case. So in single variable case, let us assume I have a nonlinear function f of x, and I have to linearize this around x naught. So f of s can be written as f of x naught plus f dash of x naught multiplied by x minus x naught divided by 1 factorial plus all the higher order terms. So when we are applying this Taylor series for linearization, we'll be using only the series only up to the first order equation. We'll be omitting all the other higher order terms. So if you are having a nonlinear function where two variables are involved, let us say f of x comma y, and when we are trying to approximate f of x comma y around x naught y naught, then this is the Taylor series expansion for this nonlinear f of x comma y. So we are going to utilize the partial fraction for x and then y separately. Again, when we are linearizing a nonlinear function, we will be using the Taylor series only till the first order equations, omitting all the other higher order terms. Now let us take a liquid level example and see how to develop the nonlinear model, and then we'll see how to linearize this nonlinear process model around one operating point. Let us assume in this process, so I have a cylindrical liquid level system and the outlet valve is giving me a nonlinear characteristics in this format. This Q naught is equal to some beta times square root of h, and we'll assume the density changes are negligible. So while writing the mathematical model, we will be writing the mass balance equation here. So rho A dH by dt is the accumulation of total mass inside the process is equal to rho I Qi, the amount of mass coming into the system, minus rho naught Q naught, the amount of mass leaving the system over the period of time. So as we assume the density variations are negligible, we can eliminate this density parameter. So we are getting the nonlinear ordinary differential equation for this system, which is dH by dt is equal to 1 by A multiplied by Qi minus beta root h. Since we have a nonlinear term here, root h, we cannot find the transfer function model directly from here. We have to linearize this ODE equation. Then we can build the transfer function model and we can do the design and analysis. So we'll see how to linearize this nonlinear model. So the nonlinear term present in this model is root h. So if you are using Taylor series for expanding this root h around h naught and neglecting the higher order terms, we'll be getting this equation. Now you can see square root h is a nonlinear term. After expanding using Taylor series around h naught, I'm getting a linear term. So this h naught is constant. For example, if you are operating your tank at around 1 meter, so all these h naught terms will be replaced by that constant. So this right hand side becomes a linear function. So the right hand side becomes only the function of h. Now substituting this in the ODE model equation, we'll be getting the linearized process model around h naught and Qi naught. Right? So dH by dt is 1 by A multiplied by Qi minus, previously we had beta root h. Now that term is replaced by the Taylor series expansion. Now this is a linear ordinary differential equation which we can simulate easily, and we can do the control system design also. Now we'll take another example of a conical liquid level system which is popularly used in many industries for mixing the chemicals. So this gives a geometrical nonlinearity to our process equations. So let us assume here I have a valve which is giving a relationship of R is h by Q naught, which is linear, and we are again assuming all the density parameters are constants. So we can write the total mass balance equation like this. Since the cross-sectional area of the tank is varying with respect to h, we cannot separate out the area parameter here. So the model equation becomes rho dV by dt, where this V is the volume of the tank, is equal to rho I QA, amount of mass coming into the system, minus rho naught Q naught, amount of mass leaving the system. So for the conical tank, at any h, the liquid volume is 1 by 3 pi r square h. So for the conical tank, we have a tank constant. So trigonometrically, if you know the maximum radius and the maximum height, for any h and r, we have this relationship alpha. So this alpha is constant for a given tank. So if I replace this volume in the model equation, finally we'll get this nonlinear ODE equation. dH by dt is 1 by pi alpha square h square multiplied by qi minus h by r. Now you can identify the nonlinear terms present in this equation, and you can linearize them using Taylor series. Now you can observe in this, h is a variable with respect to time, and qa is also a variable. So if you are observing this ODE equation, I have two nonlinear terms. One is qi by h squared, another is 1 by h. So these two terms we have to linearize now. So we are going to expand qi by h square and 1 by h using Taylor series around h naught and qi naught. And as usual, we will be neglecting the higher order terms during linearization. Now you can see the first term involves two variable case and the second term involves single variable case. So using Taylor series, we can expand these two nonlinear terms like this around h naught and qi naught. So the first equation is expansion for 1 by h using single variable Taylor series expansion, and the second one I used the two variable Taylor series expansion case up to the first order domain. So here h naught and qi naught are the operating points, so they will be constants according to our process running conditions. Now substituting these two in our model equation, this will be the linearized process model around h naught and qi naught. So you can see there are no nonlinear terms involved. We have dH by dt as an independent function of qi and h here. So now we will take a simulation example, and then we'll see how to simulate this and get the open loop response using MATLAB. Now I have a conical tank, and we got the dimension of the tank. So the tank is having a height of 10 feet and a maximum radius of 5 feet, and the outlet flow is also nonlinear. So f naught is assumed to be 2 root h, and the problem statement is we are going to simulate this for some 20 seconds when the inlet flow is suddenly increased to 5 feet cube per second. So the first step is we have to find the nonlinear mathematical model. Now writing the mass balance equation right the way we did for the previous case. So this dV by dt is equal to qin minus q out, where q out here is k root h, which is of course 2 root h, and we have the volume, and alpha is also we can calculate, which is 5 by 10 for our case. And finally, this ODE model for this nonlinear process is dh by dt is qn minus k root h divided by pi alpha square h square. Now we'll see how to simulate this using MATLAB. So I have already written this model equations. So I'm writing a function for h dot with the name contank, where we are declaring qin, which is the inlet flow rate globally, and this function is going to take time and h, the process variable. And as per the problem statement, we have the system parameter k is 2, r max is 5, h max is 10. So you can find what is alpha. This is the ODE equation. H dot is qin minus k square root of h divided by pi alpha square h square. So the system equation is written as a function here. And to give the input for this system, I have separately written a function step response. Again, here also we are declaring this qin globally because we are going to pass this input to the system model globally. And as per the problem statement, qin is 5. Steady state initial condition, we are assuming there is some liquid present in the system before giving the input, so it is 0.1. And final time, so this is the simulation time, the span, which is 20 seconds as per the problem statement. So using this initialization, we are going to call this system function using ODE23. So the syntax is ODE23, the function name where you have your system equations present, and the span, time span for which you are going to simulate the system, and the initial values for the process variables. So this ODE23 returns this time vector and the response parameter. So if you are plotting this, you can observe what is the response. So now I'm going to run this setup and let us see how the system performs. So this is the way your system behaves when I give a step input of 5 in the inlet flow rate. So your level increases from 0.1 in this station. So this is the dynamic behavior of this nonlinear system. So this way you can use MATLAB to simulate your nonlinear equations. So even if you have multi-input, multi-output case, you can simulate them like this, and the corresponding inputs you can declare here and call them using ODE23. Thank you. So these are the references used for this course. If there are any clarifications and corrections, please make me.